Hello and welcome to another video. In this video, we shall continue about the linear algebra that is used in helping us understand control system concepts. We will start with eigenvalues and eigenvectors. For a square matrix A, an eigenvector V and its corresponding eigenvalue lambda satisfy A V equal to lambda V. This means that multiplying the matrix A by a vector V results in a scaled version of V. So lambda is a scalar value. So it is a scaled version of V. So the direction of the vector doesn't change. It is only a scaled version of the vector V. And why is it important in control engineering? Because we will be able to analyze the stability of a system. A system is stable if all the eigenvalues of a system matrix have negative real parts. And also in mechanical and electrical systems, the eigenvalues represent the natural frequencies of vibration, and each eigenvector represents a fundamental mode of motion. So the eigenvalues and eigenvectors have physical significances. Now here we will see how to calculate eigenvalues and eigenvector of a simple matrix. The first step is to calculate the characteristics equation. Determinant of A minus lambda I. Lambda I is nothing but I is the identity matrix and lambda is a scalar. This is an identity matrix, 2 cross 2 identity matrix. Now substituting here determinant of A minus lambda I, after matrix manipulations we get 2 minus lambda, 1, 1, 2 minus lambda equal to 0. Now we multiply, find the determinant of this 2 minus lambda into 2 minus lambda minus 1 equal to 0. Lambda square minus 4 lambda plus 3 equal to 0. After simplification, lambda minus 3 into lambda minus 1 equal to 0. Now lambda equal to 3 and 1 are the roots, and those are the eigenvalues of this matrix 2, 1, 1, 2. For each eigenvalue, we will have an eigenvector. So here for the first eigenvalue lambda 1 equal to 3, we will find the eigenvector. To find the eigenvector, we substitute lambda equal to 3 in our lambda I minus A equation, A minus lambda I equation. So 2 minus 3, 1, 1, 2 minus 3, x and y equal to 0. Now the solution of this 2 equation is x equal to y. Hence our eigenvector will be 1 and 1. Now corresponding to the second eigenvalue lambda 2 equal to 1, we'll substitute in the equation lambda I minus A or A minus lambda I. So 2 minus 1, 1, 1, 2 minus 1, x and y equal to 0. We will get these two equations. This equation is nothing but x plus y equal to 0. So the solution is x equal to minus y. So that results in our eigenvector minus 1 and 1. So corresponding to our two eigenvalues, we now have two eigenvectors. So the first eigenvector corresponding to the eigenvalue 3 and the second eigenvector corresponding to the eigenvalue 1. And this eigenvector and eigenvalue satisfies this condition. So the eigenvalue and eigenvector satisfies this condition AV equal to lambda V. The next concept is the diagonalization and the Jordan form. Now why diagonalization is important? Diagonalization helps us to reduce the computation complexity while we calculate various exponent terms or differential equations, or while doing the stability analysis. We need to simplify the matrices. So diagonalization of a matrix is important in those cases. And what are the steps involved in diagonalization? The first step is to find the eigenvalues, like how we found the eigenvalues in the previous case. First step is to find the eigenvalues of a matrix. And then we go on to compute the eigenvectors corresponding to each eigenvalue. And then we form a matrix which has its columns as the eigenvectors. So the P matrix is formed using the eigenvectors. the columns as the eigenvectors v1 and v2. In the previous example of 2, 1, 1, 2, we had calculated the eigenvectors 1, 1 and minus 1 and 1. So the P matrix is formed using the eigenvectors. Now compute the diagonal matrix where the diagonal elements are the eigenvalues. So in the previous case, we had the eigenvalues as 3 and 1. Now in diagonalization, we express the diagonalized form of A as P, D, P inverse. So you can verify this. So this is how we diagonalize the matrix. We can diagonalize any matrix like this. Of course, you need an inverse and the matrix should not be singular. Now state space representation in control systems. The state space representation of any system is given by x dot is equal to ax plus bu, y equal to cx plus du, where x is the state vector, u is the input vector, y is the output vector, and a, b, c, d are matrices which gives us information about the system. X dot is nothing but derivative of x. We will see an example where a mass spring damper system is represented in state space form. So mx double dot, second derivative of x, plus cx dot plus kx equal to f. F is the input force. We take this variables as x1 as x and x2 as x dot, derivative of x, and we write the state space form as x1 dot x2 dot is equal to 0 1 minus k by m minus c by m x1 x2 plus 0 1 by m f, where x1 x2 are the states and f is the input. So this the representation of state space from the differential equation we had explained in the previous video. So this is how we represent a system in its state space form. In control engineering, controllability and observability are fundamental concepts that determine how well a system can be controlled and observed. They are critical for the designing stable and efficient control systems. A system is controllable if it is possible to drive the system from any initial state to any desired final state within a finite time using suitable inputs. In mathematical terms, for a state space representation of x dot equal to ax plus bu, the system is controllable if the controllability matrix has full rank. C is the controllability matrix and n is the number of state variables. If a system is not controllable, some states cannot be influenced by the input signal. So this input is what we use to drive the system from one state to another state. So from our initial state to our desired final state. So it is very important to know whether a system is controllable or not. So this controllability matrix is calculated from the information B, A multiplied by B, A square multiplied by B. So all these columns we will calculate and then we will find the rank of the controllability matrix. Now observability. A system is observable if given the system's output over time, it is possible to determine the entire internal state of the system. So this is given and it is possible to determine the entire states of the system. States are nothing but information about the internal state of the system. So for state space system with output equation y of t equal to cx plus du, the system is observable if the observability matrix has full rank. So similar to controllability matrix, we have an observability matrix which is C, CA, CA square until CA n minus 1, where n is the number of state variables. And if we calculate this matrix and if it is of full rank, then the system is observable. If a system is not observable, some states cannot be inferred from the output measurement. Why are these important? A system must be controllable to ensure that we can regulate its behavior using the control inputs U of t. A system must be observable to estimate and monitor the internal states using the output data. If a system is both controllable and observable, it is called completely state controllable and observable, meaning we can fully control and reconstruct its state. Similar to diagonalization, Singular value decomposition expresses any matrix in the form U sigma V transpose, where U and V are orthogonal matrices and sigma is a diagonal matrix containing singular values. Why is singular value decomposition important? Because we use it for noise reduction, image suppression, and system stability analysis. It also helps us in solving ill-conditioned problems. We will see an example for singular value decomposition. Suppose the matrix A is 3, 2, 2, 3. It can be decomposed into this form, where this is U, this is sigma with singular values as its diagonal elements, and this is V, and V has a transpose. So this kind of decomposition helps us to compress the image in form of image processing, and it helps us in stability analysis, understanding the stability analysis. So this singular value decomposition is an important concept in control engineering. Norms and condition numbers are important from the perspective of control engineering. Norm is nothing but norm of a matrix is a matrix measure which measures its size. So the condition number indicates a sensitivity to numerical errors. Now there is a statement that all norms are equivalent. So there are many kinds of norms, infinity norm. Out of this, we will just see the two norm, Frobenius norm, which is most commonly used. The Frobenius norm is calculated by square root of summation of Aij, where Aij is the individual elements, squaring that. And largest singular value, if you are able to find the largest singular value, that is nothing but the spectral norm of the vector. Sorry, spectral norm of the matrix. So we will just calculate, see an example where the matrix A is 1, 2, 3, 4, and the Frobenius norm is nothing but square root of 1 square plus 2 square plus 3 square plus 4 square, each elements. So that is nothing but square root of 30. So this is the Frobenius norm of this matrix A. To summarize, the matrices and vectors are fundamental tools in control engineering. The eigenvalues and eigenvector helps us analyze the stability in control engineering. And state space representation is widely used to represent the models of dynamical systems in control engineering. Controllability and observability determines the system behavior of each system. And Jordan form, singular value decomposition, diagonalization, all those simplify complex systems. Norms, condition numbers, etc. helps us to analyze the numerical stability of the system. We will see further concepts in the next videos. Thank you.